So our homework for today, how did that go? Easy, very difficult, impossible? Where does it fit on that scale? Nobody wants to answer. All right, let's take a look at it. So last time we talked about the concept of statements being collections of expressions, where an expression is part of a statement and can't stand on its own, where a statement stands on its own. All right, so we want to be able to handle this concept, and we updated our interpreter last time to have resolve statements become expressions. All right, because they would be used as part of a greater thing. All right, so we want to add to our language the ability to do some math. All right, where DoMath expressions take in two expressions and a math operator. So it's an expression followed by a math operator followed by an expression. And ultimately boil down to an int that is the result of doing the correct math. All right, and we created a README in here. So we decided that we have statements right now. We just have a remember statement that takes in a type that we're not currently using, as well as a variable name, and it's equal to some expression. And then we have a couple of expression types. Resolve expressions, which we upgraded last time. They used to be statements. And then we have this new DoMath expression, which is going to start with DoMath, then have expression, followed by a math op, followed by an expression. All right. Now, for our language right now, I think I told you, you can assume that there's always spaces between these. And what I mean by that is if you're working with something like you might have 5 plus B, something like that, that would work in a language like Java or C or C++. You wouldn't have to assume there were spaces here. Assuming there's spaces makes it more convenient for us because we can just say, here's a token. So if I were to split this on spaces, for example, I would end up with bucket 0, bucket 1, bucket 2. So I would get those pieces. All right. As opposed to if I had it like this, not that you couldn't handle it. What you'd have to do is you'd have to say, read everything here. So let's say it was 542 over there. So read in a 5, concatenate on a 4, concatenate on a 2. Keep doing that until you hit something that is a math op. And then that would be my token. Then store the math op. Then read until you hit something else. Okay. So the idea here would be is that I could handle this more complex representation of it, but for the assignment and for our language, I said you can assume that you have spaces there to split it so that you don't have to spend too much time figuring out how to split this thing apart. Okay, so let's see where we left off here. And we decided we would support plus, minus, times, divide for our math operators, as well as modulo to get the remainder for integer division. All right. So let's go into our parser initially. And let's see, we have a DoMath statement so far, but we're not using this anywhere. So that was something we started adding before we talked about expressions. Then we have this idea of an expression. And we have one expression type, that's resolve expression. So what we want to do initially is we want to update our DoMath statement to be called the DoMath expression. So I'll go ahead and refactor this. And this will be called the DoMath expression. And DoMath expressions will extend expression. And when we build this in terms of our parent, we'll go ahead and label ourselves as a DoMath expression. All right, and we'll come back to this here in a second as we start processing these, because right now this guy is just copied off of resolve expression, whereas resolve expression only needs to have a name. It needs to know what variable will I be resolving, whereas a DoMath expression is actually going to need three pieces: an expression, a operator, and another expression. So we can do something like this. We could say this guy requires a expression E1, let's call this left, followed by a string op, followed by an expression right, something like that. And then we'll keep track of expression left, right, string op for the math operator. And then we'll say this dot left is equal to left, this dot right is equal to right, this dot op is equal to op. So we'll go ahead and set those things up. I'll go ahead and dump that guy. And then for our toString for this guy, we'll go ahead and say this dot left dot toString concatenated with a space, concatenated with this dot op, concatenated with a space, concatenated with this dot right dot toString. So keeping in mind that left and right are both expressions, and expressions have a toString associated with them, either at the expression level, or if we choose to do something more direct, we can have it be more direct. Okay, so this is what a DoMath expression currently looks like, and we'll go ahead and give ourselves getters for our three pieces here. Generate getters and setters. And we'll go ahead and get left, get op, get right out of there. All right, so we've kind of built our object for a DoMath expression, but now we need to handle the idea of parsing a DoMath expression. So for example, and we're going to keep this, we're going to start by just focusing on DoMath expressions, because then they can be put into a the context of parsing a statement. All right, so what I mean by that.
I have a question.
Go ahead.
So expression, so are we considering the expression as a data type here?
Is it expression a data type? What do you mean?
Like when we say like expression left, expression right, and string op. So expression.
That would be like 5 plus B. This is the expression that's called left. This is the operator, and this is the right.
So the type is expression.
Well, yeah, because this guy can be any kind of expression. This guy can be any kind of expression. So in this case, this is a literal expression, and this is a resolve expression.
Okay, got you.
Now, we haven't actually dealt with literal expressions. I mean, I think we're just using that as the baseline. So really what we should do if we want to make this, let's say, better, is I'm going to go ahead and in my resolve expression, well, actually, I'll just do this. Inside my parser, I'm going to create a new class. I'm going to call this guy a literal expression. We've already been using these as that, but we're going to go ahead and make it a little bit more official. I think this will make the understanding a little bit better. And we're going to say that this guy extends expression. So he's everything a normal expression is. And I'm actually going to steal most of this, then we'll put it back in, or we'll update it. All right, so this guy is going to keep track of a private int value, because all of our literal expressions right now, we have a language of integers. And actually, if I want to make this guy prepared for the future, I'm actually going to call this guy a string value called literal expression. And he's going to come from expression. I think you'll see a good use for this here in a second. So we'll say value is equal to the value that was passed in. And then we'll go ahead and say this dot value here. And what I'm actually going to do is I'm going to add a getter for our value. Let me actually show you what I'm doing here. I want to show it to you as a picture. So I'm actually going to create a hierarchy. So we already have at the top level for our inheritance, we have the idea of an object. That's built into Java. Now, off that object, we have something called a statement. I think we already kind of wrote this here. We didn't quite. So this will bring some of these things. So I'm going to put object in red because we didn't write that. We wrote a statement. I'm going to make these guys yellow. We also wrote an expression. Now, under statement, under statement, we have a remember statement. So that's a kind of statement that we've defined. Now, we also under expression have a resolve expression. And we are also adding a DoMath expression. And we're also adding a, I'm going to put that, well, this will be fine. We're also going to add a literal expression. But literal expression is also going to be a parent class. Because off of that, we're going to have a int literal expression, which is a literal expression. This will give us the ability to later have char literal expressions, float literal expressions, so on and so forth. So this guy is actually never going to be instantiated. This is never going to be instantiated. This is never going to be instantiated. These three classes exist for us to have other classes built off of them. All right, and let me see if I already made our other ones abstract. So if I go to expression here, yep, so we talked about this last time. So expression is an abstract class. That's why I have it in yellow here. So I'm saying we can never actually create one of these. To create expressions, we actually create resolve expressions, DoMath expressions, or int literal expressions. Similarly, we can never actually create literal expressions. They are just the intermediate step to get from a generic expression to an int literal expression, or yeah, something like that. All right, so as we're writing that, if I go back to my literal expression here, I'm also going to make this guy an abstract class because we do not intend to actually make generic literal expressions. Instead, we're going to make int literal expressions initially, because that we only have a language of numbers right now. All right, so we're kind of building our language up, and this shows us a current picture of our language. So anything in yellow, I'll mark this. These are abstract classes. Anything in green are usable classes. And then we'll go ahead and throw the, just to have our full answer key thing here. These are Java defined classes in red. All right, so we didn't write this. We wrote this without the intention of directly using it. All the stuff in green we wrote in terms of the abstract classes we created. All right, so this is just an object-oriented approach. And we're doing this from, now we focus on the language design aspect of this. Last time we talked about our statements are a collection of expressions where we have three different kinds of expressions. We have a resolve expression, which resolves the value of a variable. We're in the middle of building a DoMath expression. And then we went ahead and actually gave real meaning to our int, our literal expressions, instead of just saying, well, if it's not one of the other kinds, it must be a literal. All right, we're going to go ahead and now give some meaning about which specific types we support. So I'm kind of adding an extra step in on top of what we were doing for the homework here. So let's go finish writing our int literal. So this is just a generic literal expression, and that guy is going to be abstract. I'm going to steal most of this. And we're going to go ahead and we're going to create a new class, and we're going to call this guy an int literal expression. I'm actually going to put a little underscore in there. Int literal expression. Yeah, I like it like that. All right. And we're going to say that this guy extends literal expression. This guy will take in an int as a value. Int as a value. he'll return an int. Yeah, I don't think it likes me calling this just value since I'm getting that from my parent. I'm actually going to leave it as a string. And when we get the value out of this guy, we'll return it. All right, so we'll read in an int value when we're storing an int literal. We'll go ahead and call our parents constructor. Our parents constructor for literal expression requires us to pass it I'm going to pass it to this. Show you literal expression. Literal expression takes in our string value here. So actually it's going to need to take in one other piece. So it's going to take in a string. Actually, you know what? I'm gonna just go ahead and let it do its thing with literal expression. But one thing we do need to do is value here for literal expression. Because we want to have access to it in int literal, we need to make this guy protected. Then we'll get access to that value inside of int literal expression. So an int literal expression will take an int as a parameter. We're going to go ahead and store it as a string inside of the variable that we already received here. But actually what we're storing as a string is this guy. And you know what? We're actually going to do this. I'm going to pass it in as an int. Inside of a literal expression, I'm going to go ahead and have another version of this constructor. This guy will take in an int. He'll store himself as an int literal. And then we'll actually, under the hood, store it as a string. But we're going to build it from an int literal expression, who will call his parents constructor, passing in an int. We will then let expression know we're actually an int literal expression. I think I did like an underscore like that. And then we'll set this guy's value to the string version of this int. So now I have two different constructors here. One that takes in a generic string, which we actually will probably use in the future if we have time to store string literals. And then another one that takes in an int, which we then go ahead and still store as a string because that's the kind of way we store stuff in our language. But ultimately, if I'm dealing with an int literal expression, though, when I call get value, I can go ahead and I can return an integer from this this guy. Now, what's this complaining about here? Right.
Maybe you should change it to protected in the parent class.
I already did. Literal expression. I already
I
made.
mean the get value.
Oh,
Yeah.
oh, thank you. Yeah, otherwise I wouldn't have access. Well, actually, hold on.
I think it's because here you said it's a string type, so you cannot change a type.
Let's see. Polymorphism says that it has a different name and or type of parameters. Oh, not necessarily the return value of it. So then what I'll do is I'll leave it like this. And we'll go ahead into here and we'll have this guy say get int value, and he'll return the parse int of this dot get value to be more specific, even though it's just directly accessing that variable. So this will allow us to specifically get the int value from a, you know what, I really don't like that though. I want to be able to ask all expressions to give me their value. That's what I want. Now, realistically, I'll never actually get the value from a generic literal expression. So this guy would never actually get called. So when I get the value of one of my specialized literal expressions, it'll give me the value as the correct type, which right now is going to be a int. Okay, so that is int literal. Now let's update our interpreter to work for that guy before we dive into our DoMath. Now this might not have been the way you did your DoMath. I'm just kind of skipping the step of just assuming it's a literal if it's not a resolve. So I'm making it a little bit, I'm kind of doing the homework plus some, rather than do the homework and then fix it for some other things. All right, so I go into my parser. And we're reading stuff in, we're putting it into our file contents. We're then splitting it on the semicolon for our individual statements, because we've set our program as a collection of statements, and a statement is a collection of expressions. Then we call parse statement. So parse statement takes the current string that's in our statement, splits it on white space. And if we're looking at a remember, then we're going to go ahead and parse a remember. If we're not looking at a remember for right now, we must be looking at, well, actually, that's the only kind of statement that exists right now. So it must be a remember right now. All right. Now, for list of statements, we call parse remember, passing it the three pieces. Keeping in mind, now let's give ourselves an example here, because we're splitting this on white space. What if our, this is where we become more complicated. What if we say something like remember int b is equal to 5 plus a. I think we call this do math, do dash math. 5 plus a. This is a legal statement, correct? And right now we're splitting this guy on the parts. and we're deciding that, oh, part at bucket 0 is a remember, which it is. But then I'm saying, okay, well, let's go ahead and parse remember. So I'm passing it the int, I'm passing it the b, and then I'm passing it the value, the thing that's on the right hand side. But the problem with that is I can no longer just say the parts is equal to 4. That presumed it was a literal value before. All right. Now, what do I mean by that? I mean, if I have my parts right now, the parts at bucket 4 would be, this is 0, 1, 2, 3. I would be passing it the word DoMath. Well, really, I need to parse this entire expression, the stuff that comes after that equal sign. That's the value that should be passed in here. Does that make sense? So what I need to do is I actually need to turn this guy. I need to parse expression on this guy, but not just on part 4. This is part 4. I need to get it on all the rest of the parts. So from part 4 all the way to the end. That makes some sense? Okay, because this guy is no longer ready to be passed in. He needs to turn into what he's going to be, which is a set of objects. All right. Now remember, my list of statements, we're adding a statement to this guy. So in this case, we're adding a parse remember, since that's my only kind of statement. But I need to get the value on the right-hand side instead of just assuming it's a literal, a non-object literal. We just invented our literal object. Instead of assuming that's what it is, it can be all sorts of different types of expressions. So we need to be able to handle this. We need to say, okay, everything after the equal sign here is my expression. And I need to then parse that expression. So here's parse expression. This guy is going to take in a expression as a parameter. Now, right now, we only know about resolve expressions. But what we really need to do is we really need to look at what this expression actually has in it. So let's go ahead and let's package this guy up. Parse expression ultimately boils down to something that is an expression. So we're going to say parser.parse expression, and I need to pass this guy a string. All right, and I want to pass him the string, everything after the equal sign, probably trimmed. All right, so string, the expression part is equal to, actually, let me start off. I'm just giving myself a couple of variables here. Int pause of equal sign. I don't think I can say that. So pause of equal sign is equal to s dot index of equal sign. So that's going to tell me where in my string is that equal sign. Okay. And legal syntax in our language right now says that you can only have one equal sign. Okay. At the very least, that's going to be the index of the first one, because as we kind of move ahead and start thinking about Booleans, we potentially could have something like remember int b is equal to a equal c, something like that, where we assume both of these guys are Boolean types, and we're well, actually, we assume that these guys are integer types, and we are able to get a Boolean result from them saying, is this guy equivalent to this guy? In that case, it would boil down to true, which is that's what we would remember inside of B. But notice here, I actually have 3 equal signs in this guy here. But index of gives me the position of the first one we find. Okay, so this would still work for that. So I'm going to go ahead and see where is the position of that equal sign in S. And then I want to call this, I want to say string everything after the equal sign. I'm really specifying that, quite a bit here. So I'll go ahead and say S dot substring, and I'm going to say pos of equal sign plus 1. So everything after the equal sign will be a substring of S starting at position of equal sign plus 1. And then what I'm going to go ahead and do, just to get any extra spaces from the beginning or end off of there, I'll just trim it. Because what that would end up giving me in this case, the substring would give me that. Trimming the whole thing will give me this piece. In this example. All right, so this is actually the expression on that right-hand side of the equal sign. That's what we're dealing with over there. And what do I do to expressions? I call parse expression on those. That's the expression I want to call parse expression on. All right, I am going to have to update parse remember to no longer be expecting a string here. Where is my parse remember? Parse remember is taking in a string, a type, and then now it's taking in an expression, the value expression, something that is an expression. All right, which we haven't parsed yet, but that's what this guy will ultimately end up being. All right, so we'll go ahead and call our resolve expression on that expression. Actually, right now we're assuming it's a resolve expression on that value expression. So really, this is where we need to be a little bit better. We're calling parse expression outside of this. So it's actually already coming in as an expression object. So that's what we called RE here, except instead of assuming it's a resolve expression, now we're saying we're going to go ahead and create a remember statement with the type, with the name, and then the value expression. That's what's going into my remember statement. Remember, we are not ready to execute that value expression yet. So if I come back over here and we look at a remember statement, remember we're still inside the parser. The steps are syntax, goes through the parser, which turns it into objects, which then can be executed by the interpreter. All right, so a remember statement takes in something that is an expression. Before, we were always passing it a resolve expression because that's the only kind of expression that existed. Now we're going to have 3 types of expressions: a resolve expression, a literal expression, as well as a DoMath expression, which is what the homework was. Okay. So that's what we're going to get from our remember statement. So we changed this guy. We actually didn't change the remember statement itself. We just changed the possible things that could be passed in here. Before it was just a resolve expression. Now we have two other kinds that can be passed in. Okay, so we're taking something in that is an expression. So we want to ask, well, we can actually just go ahead and pass that expression through here. So this actually is done, our remember statement. So now what we need to do is we need to handle our resolve, or we need to handle our expression. So what does parse expression do? Parse expression right now takes in an expression and just assumes it's a resolve. We need to ask a little bit more about this guy to find out what kind of thing is it actually. Because right now it can be a, we'll say, possible expression types. It could be a DoMath. It can be a resolve, or it can be a literal. Those are the types of expressions we currently understand. All right, so what we're going to do here is we're going to split our expression on those empty spaces, just like we did before. And the name of our string is called expression. All right, so we'll split that on there. Now, if it's DoMath, that one's the easy one. We'll see a DoMath at the beginning of it. Now, for right now, I'm actually not going to write the, well, I'll write the DoMath part. We just won't use it yet. So we're going to say if the parts at bucket 0 dot equals DoMath, then return a DoMath expression. Haven't written that guy yet. All right. Else, if the parts at bucket 0. So how do I ask the question, is this guy a is this guy a variable name? How do I ask the question, is this a variable name?
So it's in like variable environment.
Well, we can't look for it in the variable environment until, because remember, we're still parsing here. This is not interpreting yet. So we're looking at something. So variable names are going to look something like B or A. They won't look like a 5, or we don't support chars yet, but or a D. So this is a variable name. This is a variable name. This is an int literal. This is going to be a char literal later on. So what I'm asking here is, how do we identify the difference between, you know, these 4 things? I mean, we could pretty easily say, is this guy equal to a number, right? So we could say if this guy so this would be character. Well, let's see. We'll do is digit. And the character I'll give it is that string dot char at 0. So for instance, if I was giving it a 5, this is bucket 0 of that string. I'm asking, is that a number? If it was a 532, bucket 0 of this string would be the 5. I'm saying, is that a number? So I'm saying if this guy starts with a digit, it must be a int type. All right, so if this guy starts with a digit, that's what this is asking. If it starts with a number, what am I missing here? This closes that one, that closes that one, that closes. If it starts with a number, what kind of expression am I returning? I'm going to return a int literal expression. Return a new int literal expression. I'll go ahead and pass this guy. And let's look at my int literal expression real quick. Constructor for this guy takes in an integer as a parameter. So I'm going to go ahead and give it as a parameter. So I'm going to parse this value, integer.parseInt, and that's the guy I'm parsing. All right, so if I'm looking at something that is a number, I'm going to go ahead and build an int literal expression from that number. And that's what I'll return. Else, if it's not a DoMath expression and it's not a number, it must be a variable name. So I'll go ahead and return parse resolve on that guy. Let me just look at parse resolve real quick. Parse resolve just creates it out of that. I probably, just to be consistent, I want to go ahead and say literal expression, parse literal. Take in string value. And right now we only have one kind of literal, so we'll return a new int literal from integer.parseInt of value. So same logic as I had before, just down here, what I'll do is rather than do this, I will return parser dot parse literal of in this case, it would be my entire expression. The entire expression is my literal value. So this is a variable name. This is a must be a literal type. And this one is must be a DoMath type, DoMath expression. All right, so we haven't written that part yet, but now we have this guy is returning for our parse expression. And I'm gonna just, for the time being, I'm just gonna say return null here. That'll make this guy happy because we promised we'll return a value. Okay, so parse expression, it's going to return some expression here. It's going to take it a string representation of the expression. It's going to find out what kind of expression it is. It'll find out if it's a DoMath, which we're not handling yet. It'll find out if it is a int literal. If it is, we'll parse our literal. We'll return an int literal. So this is the new thing so far. Otherwise, we'll return parse resolve. All right, so this is just calling parse on it. So I want to test this now. Let's go back to input spider. So we have, remember, int a is equal to 5, all these things like that. So now what we want to do is we want to go ahead and just parse this and then view the output of the parser to make sure that it's treating this guy is a literal, this guy is a literal, and this guy is a resolve expression. So we'll go ahead and ask our parser to display. All right, so remember statement int a is equal to an int literal expression 5. Remember statement int b is equal to int literal expression. Remember statement int c is equal to our resolve expression. So it seemed to get the pieces correctly for us. All right, so it's parsing those correctly now. And now we just need to update our interpreter. Because right now our interpreter doesn't know how to get the value from a literal expression. So we're going to go ahead and go into our interpreter. And we're going to interpret statements. So right now we're assuming it's a remember statement, which that's our only kind of statement so far. So it must be a remember statement. So what do we do to remember statements? We interpret remember statements. Here's our interpret remember statement. So we go ahead and we get the expression from our remember statement. So now this guy can be one of, this exact second, he can be one of 2 different types of expressions. He can either be a resolve expression or he can be a int literal expression. All right. So right now we're asking the expression value, we're passing it that value expression. So we need to go into get expression value and allow this guy to handle, right now we're assuming that all our expression values are just integers. Because we have a language of integers, which we're okay for right now. That's compatible with what reality says. So we're going to go and look at get expression value, which is this guy, and he's taking in some kind of expression. We're saying if it's an instance of resolve expression, then we'll go ahead and return the interpret resolve expression. Now, it could then also be a instance of a int literal expression. So here's our interpret resolve expression. I'm going to just steal. Let me think about this. Yeah, we're going to take that piece out. So we're going to interpret a literal expression here. And we're going to say if LE is an instance of int underscore literal expression. If it's one of those guys, then we're going to go ahead and return le.getValue, the integer of that. Otherwise, we'll go ahead and throw a new runtime exception. Not a valid literal type. And then I'll actually we'll just leave it alone for now. We'll just say it's not a valid literal type. Because right now we only have one kind of literal type, an int literal type. So when we interpret our literal expression, it's ultimately going to give us an int right now, even though we intend to have other kinds of literal expressions in the future. So get expression value is going to take in a type of expression. We're dealing with a resolve expression sometimes. So we're saying if it's an instance of resolve expression, return that. Else, if E is an instance of literal expression, return spider interpreter dot interpret literal expression. And this guy will boil down to literal expression E. So if we're looking at a literal expression, then we'll return whatever interpret literal expression returns, passing it E as a literal expression. That closes this, so we have an extra one there. Okay. Otherwise, it's not a known expression type. So we have one new expression type here. And that's our literal expression. All right, so now we have added A = 5, B = 7, C = 7 to our variable environment. All right, so now we've processed those literal values. Let me look at my input.spider. Yeah, C = B, so we got the 7 added there. So it handled a resolve expression. It also handled 2 int literal expressions. All right, so what we've done up to this point now is we've updated our interpreter from last time to work identically to how it worked last time, but now it has a second expression type called a literal expression, which within that has a single int literal type called an int literal expression. All right, so now we're more fully featuring the idea of expressions as make sure it's not from this class. So we're now dealing with expressions in, Dr. there. Okay, so now that we have that, now we can go ahead and add the DoMath portion of this, which is what our homework assignment was. So we already started our DoMath expression. Our DoMath expression is going to take in whatever the expression on the left is, whatever the expression on the right is, as well as an operator. We're going to go ahead and advertise ourselves as a DoMath. Then we'll set the left, the right, and the operator. Okay. So then we'll go into our parser. So up here in our parse expression, the expression could be a DoMath expression. If it's a DoMath expression, then we have to parse a DoMath, passing that expression. So I'm going to add a static. The DoMath expression parse DoMath. All right, and this guy is going to take in so in order to do math, we need to, well, actually, I'll just go ahead and take in the entire expression here, and then we'll work with it, because that's how we've done it for literals, and partial numbers didn't require any individual pieces. So we're going to go ahead and take in a string expression. All right, and his job will be to break it into its well, I guess into its pieces, keeping in mind that we're going to have a math operator in the middle. So what this guy is likely to look like is something like a plus 7, something like that. And we want to parse that into a resolve statement, a plus, and a int lit expression 7. That's what we want to turn it into. So we need to call parse expression on this, parse expression on this, and then keep our math right here. Now, realistically, if we just I think I told you for the homework, you only had to handle one level of this. But let's assume that what I'm looking at is actually something like this. DoMath. So what if I'm looking at something that says DoMath a plus 7 plus 4. So here is a DoMath right there. And this whole thing is also a DoMath. So we would need to be able to handle it going into this one additional depth to be able to handle real statements. So like if I was in Java, I should be able to say something like int a is equal to a plus 5 plus b. So this whole thing is a math expression containing a left operand of that math expression and a right operand of this resolve expression. All right, so think about that. For the homework, I mentioned that you could assume there would only be one math expression. For your next homework assignment for Thursday, we're going to be adding in that additional layer of a math expression, but I'll get our interpreter up to what was due for the homework for today. All right, so doesn't work for this yet. Will work for this. Okay, so we want to turn something like this into those components from that expression. All right, so I'm going to go ahead and split this guy on his pieces. And I'll steal our all right, so I have my expression split on this guy. Right now, we are assuming only a single level of DoMath. Okay, which means that our expression currently looks something like this. So we know that bucket, well, we know that bucket 0 is my DoMath, and we know that bucket 1 is a variable name, or it's a int literal, and we know that bucket 2 is either a variable name or, well, actually we know it's a math operator, and then we know that this guy is either a resolve expression or a int lit expression. All right, so I need to go ahead and I need to return a new, actually, let me go ahead and let's just get the pieces. Expression left will be equal to parser dot parse expression, and I want to give it the left portion of this guy, which will be the parts at bucket 1. So if I split this guy up, I'm asking him to parse this expression. That'll give me my left expression. String math op will be equal to the parts at bucket 2. Expression right is equal to parser dot parse expression of the parts at bucket 3. So I'm saying, remember the plus sign, that's called math op. Parse expression this guy into whatever he gives me. Parse expression this guy into whatever he gives me. They're going to give me some kind of expression. And then remember, we built a DoMath expression. DoMath expressions are built with an expression, an op, and an expression. So I'll go ahead and return a new DoMath expression, passing it my left, my math op, and my right, because that's what this constructor took for a DoMath expression. So let me walk through this, because this should have been the secret sauce for the homework assignment. I'm taking in a string expression that looks kind of like this. And actually, let me put this up here. Of work for homework. All right, so I'm taking in something that looks like this. And I want to get left to be the result of calling parse expression on that, which should give me a resolve expression. I want to get my math op, and then I want to get the result of calling parse expression on the right half, the right portion of my expression. And then I'll go ahead and build a DoMath expression object out of those 3 pieces. And that's what parse DoMath will do. If I'm down here inside of parse statement, well, actually, I'm sorry, parse expression. If I'm dealing with a DoMath expression, then what do? I'm going to return parser dot parse DoMath my expression. So if I'm looking at a DoMath, call parse DoMath. If I'm looking at an int, call parse literal. So if I'm looking at a literal, call parse literal. Right now we only have one kind of literal. All right. Otherwise, I must be looking at a resolve expression. So one way or another, when I parse an expression, I'm going to return an object of type expression. And what objects do I have that are of type expression? I have this kind, or this kind. Those are my three possible expressions that parse expression could return. That's returning them as objects so that our interpreter can use those. Okay, so now let's go back here to our input.spider. And I'm going to say something like DoMath A plus B. So what we should get from this parser is this guy is a remember statement whose value is going to be the result of DoMath expression with a resolve expression and another resolve expression. So let's test to see if our parser is working for that so far. So I'll tell our parser to display. We're not interpreting it yet because we haven't written that portion of the interpreter. So we have a remember statement, and then the last one is a remember statement where int C is a DoMath expression, where the expression is a resolve expression, and the other expression is a resolve expression with a plus sign in between. All right, so I seem to be parsing it correctly now. Okay, so now that I appear to have my pieces parsed, I can now go into my interpreter. And let's make our interpreter work for this guy. So here's my spider interpreter. I'm interpreting a remember statement. So this guy is going to go ahead and get my value expression, which is going to be in this case, if I'm dealing with a DoMath, we'll just pretend because we know it works for the other ones. This guy will be a DoMath expression. And then we're going to ask our spider interpreter to get us our expression value from that guy. So here's our expression value. So if it's a resolve expression, do this. If it's a literal expression, do this. Else if E is an instance of DoMath expression, then we're going to call interpret math expression. So I need to write that. A private static int interpret math expression. This guy will take in a DoMath expression. DME. All right, and his job is to get the two sides of that guy. So we're going to go ahead and say expression left is equal to DME.get left. Expression right is equal to DME.get right. And then string op, we'll call it math op, is equal to DME.get op. This is the math we're ultimately going to do. but we need to get the value for our two expressions here. So I need to go ahead and call expression value for each of those. And this guy's called spider interpreter, right? So we'll say int left value is equal to spider interpreter dot get expression value left. We're going to do the same thing for right. Get the expression value for right. All right, so left value and right value should now be a number since we only have a language of numbers. That's why I assumed it's going to be an int. All right, so how do we get the value of an expression? I know left is some kind of expression. How do I get the value of an expression? Asking my interpreter to get me the value of an expression. How do I get the expression to the right? How do I get its value? Ask my interpreter to get me the value of an expression. Pass it that expression. So now I have a left and I have a right value. And now I want to actually do the math. If mathop dot equals a plus sign, return left value plus right value. Else if it's a minus sign, return the minus. Else if multiplication, then we'll multiply them. Else if division, we'll divide them. Else if this guy, modulus, and we'll mod them. Otherwise, we will throw a new runtime exception, not a valid math operator. Math op. All right, so we'll just ask a series of questions. So we have our left and our right value. Then we'll do the appropriate math for what that left and right value were. So given our current code, do math A plus B, we should get a value of 5 and a value of 7, and that is 12, right? So this should give us a C is 12 in our environment. Let's see. Not a known expression type. Do math expression. Okay, that's one of our error messages. It's inside of Git. So that's in here. Oh, I didn't write that part yet. We need to return spider interpreter dot interpret do math expression, passing it a do math expression. All right. Now we get our C is 12, the result of our DoMath expression. And I should be able to do like another, remember, D is equal to do math for -2. So that should give me a 2 for that guy. There's my D is equal to 2. Let's make sure we can mix and match. And E is equal to do math. Let's see, 10 divided by A. 10 divided by A should be 10 divided by 5, which should also give me a 2 inside of E. There's E is 2. Let's do 10 mod A should give me a 0. Because 10 divided by 5 has a remainder of 0. There's my 0. Multiply should give me a 50. I think I've done all of them. And then here, I'll just put a bad math operator in there. And now it should scream at me saying, not a valid math operator, question mark. Okay. So that should be the result of the homework. And then some, because I've also added the ability for us to handle literal expressions. So questions about that so far? That was fairly complex what we just did, I'm guessing, for a lot of you. It wasn't hard stuff. It was more organizing stuff. So the part, well, let me take a sip. What you really want to focus on here is this idea of what we did to draw pictures. So what did we write today? We added this whole idea of literal expressions and int literal expressions. We did that first. So that was something I did not ask you to do for homework, because we were already handling int literal expressions as anything that wasn't a variable name. So you probably did this homework without this piece. This piece was something that's going to be beneficial for the next assignments. Okay, so just trying to keep track, because obviously when you just sit here and watch me write just a wall of code, it might be a little bit hard to follow, right? You're gonna have to go back through, look at it yourself. Maybe I went too fast, whatever it is, that's why I record it all. But obviously, we added, I don't know how many lines of code we added. We can probably check. Let's just go into this here. Here's our interpreter. So we updated driver, we updated spider, we updated our spider interpreter. So that's all of our new stuff inside of spider interpreter. So we fixed our added literal expression, added DoMath expression, and then handled our interpret resolve expression for literal and DoMath expressions. You can see what we've changed in these files. This was inside of Parser. We created a class called DoMath expression, which is an expression. Here's our int literal expression. Here's just our literal expression, which is abstract. And then this is what we changed in our parser. So in the end, we didn't actually write that many lines of code. It was just certain lines of code that were pretty important. And unless you're drawing pictures like this to kind of keep yourself on track, right? This is what we currently look like. These are the objects that currently exist inside of our parser. And then our parser takes these objects and actually does math with them. And hopefully you see that the interpreter takes these things and does the math with them. Hopefully you see that the interpreter itself is much less complex than the parser. The interpreter itself, I mean, think about how much of this code is just these if statements asking what kind of stuff it is. So once we get things broken down into our statements and the expressions that those statements are collections of, we can actually do the logic of the interpreter pretty easily. So one thing we want to really appreciate here is this idea of syntax goes through a parser which comes out as a list of statement objects which is a list of expression objects. So a list of statement objects is each a list of expression objects, which the interpreter then interprets into resolved output. That's the process. We write our code, we parse the code. So if you notice each time we've made changes here, what did I do? I went into driver and I commented out these things and just tested my parser. I want to make sure that my parser is doing its job before I start writing my interpreter to interpret the results of the parser, where the results of the parser was a list of statement objects containing its corresponding list of expression objects. Once I know this is good, once I have a list of statement objects, and that's the result of my parser. So if I show you right now, my parser looks like this. So I have a list of statements. I have a remember statement, a remember statement, a remember statement, a remember statement, and a remember statement. All right. And each one of those guys has expressions in them. Literal expression, a DoMath expression, another DoMath expression, another DoMath expression. That's what this is right here. The result of my parser. This thing here has to be correct in order for this to work. If you're feeding your interpreter bad objects, it's not going to be able to do its job. That's why I'm always testing the output of my parser first. And then once I'm confident that my parser has given me good stuff, then I can go and add stuff to my interpreter so that my interpreter can actually go through and do the stuff it's supposed to do, ultimately giving me my resolved output. Which was this. This is just showing me the resulting variable environment after I did all that stuff. And then it happens to be showing me this hidden output, because remember statements actually don't show anything on the screen. They just are hidden output. So it's just showing me that the result of that first one was added 5 to the variable environment. The result of the second one is I added 7. Result of the third one is I added 12, which is the sum of these two. So this was the result of doing some math. The result of the next one, I added 2, also the result of doing some math. Next one, I added 0, next result of doing some math. So all of these resulted in nothing I would actually see on the screen in a program, but just adding a bunch of stuff to my variable environment, which we see that it did. All right, so that's the result of my interpreter interpreting the objects that the parser created. All right, so questions about what we have so far.
Would you mind to explain one more time assignment parts, homework part?
We'll say this again.
Can you explain homework parts?
Okay,
Yeah.
so if we walk through, so again, the first step was to update our parser, right? All right, because we added a new kind of syntax. So the first thing we had to do is we had to update our parser to handle this new kind of syntax. So let's look at that first. So I went into my parser and I created a DoMath expression. So, well, let me show you what I did first today, because I also created a literal expression. So the first thing I did today was I created this guy, and then I created this guy.
Okay.
All right. I created an object to represent literals, which we already were supporting in our language. We just treated anything that wasn't a variable name as a number. That's what we were already doing. Now I said, well, it could be any kind of literal, but by the way, that only kind of literal is a number right now. So I just more formally did what we were already doing, but let me show you what I did for that. So we created this idea of a literal expression. And you see, this guy is super simple, right? There's nothing much to him. So his name is a literal expression. He's an abstract class, which means we cannot directly create instances of him. Notice I have him in yellow here. Yellow means abstract classes. We can't make these guys. Instead, we create instances of specialized versions of them, like an int literal expression. Okay, so he's an abstract class called literal expression, and he is an expression. He extends the idea of a generic expression. So literal expressions will hold our value as a string. And I'll go ahead and when I construct it, notice I can construct literal expressions two different ways right now. I actually only need to construct it this one way. I just started off with also having a value. So this is a generic literal expression, which we should never see. We should never create one of these. All right, because nothing is actually a generic literal expression. Things are all specialized. So we can actually dump this if we wanted to. See, we're still good.
Wow.
Because we never actually created one of those. Our only actual kind of literal expression is ones built with ints right now, because that's what our picture says. The only special type of this guy we have is an int literal expression. Make sense?
Okay.
All right, so here's the constructor for our literal expression, takes in an int, lets him know that he's an int literal expression, and then just sets the value to the string version of that int, since we're storing everything as strings for convenience right now. And then he has a little toString. So that was our generic literal expression. Then we have our int literal expression. Notice also pretty simple, right? Not a whole lot of code here. This is just your stock class. So we have something called an int literal expression, which extends literal expression. So we have an expression. We have int literal, which extends literal, which extends expression. So actually, if I were to draw this a little differently, I'd probably draw it like this. Something like that. These are the kinds of expressions we have. And then here's an even more specialized. All right, so int literal takes in an int value and just passes that on to the parents constructor, which sets up that int literal. And then we have our toString for this guy, and then we have the get value, which gives us the integer version of this. So just an object for holding literal expressions. Okay, so then inside of our parser, Well, here, let's go ahead and show you the DoMath part too. So then for the homework, we also created another kind of expression called the DoMath expression. And the DoMath expression holds three pieces of information: the expression on the left, the expression on the right, and whatever the math operator was. Those are the pieces that it holds. When I create an instance of a DoMath operation, I need the left, I need the op, I need the right. So I build it using those three pieces of information because that's what a DoMath expression is. Remember, this is my parser I'm looking at right now. That's this guy. His job is to give me things that this guy can then eat, can then interpret. All right, so the job of the parser is to give, if I'm looking at a DoMath expression, is to give me a DoMath expression object in my list of statements and expressions. So here's my DoMath, holds these three pieces of information, gives me the right setters and getters for them. All right, so a DoMath expression holds a left, a right, and an operator. An int lit expression holds an integer value, and a resolve expression holds a variable name that will be later resolved in the variable environment. So those are the three types of expressions that we have. What does our parser do? What did we add to our parser? We added a function for parsing DoMath. So if I happen to identify something as a DoMath expression, I read it in here, I split it, I grab the left, I grab the operator, I grab the right, and then I create a new DoMath expression with those pieces. That's what I do if I'm parsing a DoMath expression.
What would the new keyword would do with the DoMath expression?
This creates an instance of it. So this guy creates and return an instance of DoMath expression. So this guy right here, I can put it in 2 lines if you want. DoMath expression result is equal to that. And then I can return the result. So this creates an instance of a DoMath expression, and I store it here in this variable, and then I return the value of that variable. Because that's what parse DoMath does. It takes in a string and it spits out a DoMath expression object. Make sense?
Yes.
Similarly, if I'm parsing a literal, I take in a string value. Right now, we only have a single literal type, and that is an int literal. We could add to that later, but right now we only have one kind. That's why we don't have any if statements in here. Make sense? If we're in here, it's an int literal, or it's a syntax error. Okay, so that's for parse literal. Parse remember already existed. Here's our general parse function that already existed. We didn't do anything special there. For parse expression, we did add a couple of pieces here. We added this first if and else if. So we said, if the beginning thing is DoMath, well, go ahead and return parse DoMath, which we just looked at. If the beginning thing is a number, go ahead and parse that literal. Otherwise, it must be a variable name, so go ahead and parse resolve. So these guys, one way or another, are going to boil down to an expression, and that's what parse expression returns. He takes in a string, and he gives us the appropriate expression for whatever that string is. Note here that we never get a generic expression. This guy will always return either a resolve expression, a DoMath expression, or an int literal expression. He'll return one of those three. So here's when I return a DoMath. Here's when I return an int literal. Here's why I return a resolve expression. That's what parse expression does. It takes a string and gives you a expression object. Parse statement didn't change. We still only have one kind of statement in our language called a remember statement. All right, so that's it for parser. So that's all we updated to go from here to here. So that part makes sense so far?
Yeah.
Now, I do recognize that this is starting to feel complicated, but if you only look at one thing at a time, for instance, if you're only looking at this function, a function whose name is parse expression, he takes in some syntax and he gives you an expression object. That's his single job. We're only asking 3 questions in here. We're getting our parts. Is it a DoMath expression? Is it an int literal expression? Or is it a resolve expression? That's all we're doing. And this is like making a little widget from Home Depot that I can throw a line of code into, and he will give me that guy wrapped up in a nice expression object. So that's the job of this little piece. So this is us writing modular code that allows us to write these individual functions. We're not doing too much in any individual function. This guy's job is to parse an expression. What does it mean to parse an expression? It means to take in some code and turn it into an object. That's what it does. Similarly, we have a parse statement. What does parse statement do? It takes in some code and ultimately adds a statement from that code to our list of statements for this program. Because that's what a parser ultimately does. A parser ultimately gives us a list of statement objects, which is a collection of expression objects. All right, so that's for everything up to this point. So now what do we do with this? This we then throw into our interpreter, which then gives us some output. So let's go look at what we did at in our interpreter. Here's our interpreter. Display results didn't change. Same thing we wrote before. We're still calling interpret on a list of statements. That didn't change. We still only have one kind of statement, a remember statement in our language. That'll change. We'll get to our homework for next weekend. We added this guy. This guy says, hey, if you need to interpret a literal expression, you go ahead and give me a literal expression, and I will give you the int version of that guy. Right now, we know it's an integer because that's the only kind of values we support in our language. So we're going through the motions and saying, well, if it's an integer, so if you handed me an int literal expression, then I'll go ahead and give you the value of that guy. Otherwise, I'm going to scream and yell that this wasn't a valid literal type. All right, because we only have one kind of literal. So that's what we added for interpret literal expression. So nothing crazy here, right? You give me an object containing an integer, I'll just spit out the integer that was in there. That's how I'm going to interpret that. You're holding a 5, I don't need to do anything special. I just say it's a 5. Here's your 5. Go do whatever you're going to do with it. Interpret DoMath expression. This guy's going to take in a DoMath expression object, which our parser built. And what is he going to do? He's going to extract the left expression, then he's going to interpret that expression. He's going to extract the right expression, then he's going to interpret that expression to get the value from that. All right. Then he's going to extract the math operator. Now he has the value of the left and the value of the right because we've interpreted those two expressions. Now we ask the question, you want to do addition? Do addition. Subtraction, do subtraction. Multiplication, do multiplication. Division, modulo. If you didn't give me one of those, I'm going to scream at you and say, hey, that's not one of the math operators I support. Okay. I think so. Then we also added to get expression value, because now we have a new type of expression value to get. That is the value of a DoMath expression. Notice that our expressions right now always boil down to integers, because we have a language of numbers right now. So we're saying, hey, if it's a resolve expression, go and interpret a resolve expression, which we'd already written. What does that guy do? He goes and looks up the variable name in the variable environment, gives you the value associated with it as an int. That's what he does. If it's a literal expression, what do? Well, we go ahead and we'll interpret the literal expression. We just looked at that. What does he do? He just gives you the number that's stored in there. If it's a literal expression object that holds a 5, it'll boil down to a 5. That's what he does. Otherwise, if it's a DoMath, we'll call interpret DoMath, and we just saw what that does. It pulls out the left expression and the right expression, interprets both of those, gets the value of both of those, and then does the appropriate math on those results. That's what that guy does. All right, so that's walking through everything that we did. We wrote this piece first, then we wrote this piece. That make sense?
Do we need to think about the priority of the operators?
For your homework, no. So what he's asking here, let me move this up here. Homework, add the ability to have multiple math operators within, I'm sorry, multiple DoMath expressions. Within a DoMath expression. So you should be able to do something like, remember int a is equal to DoMath b plus 5, let's see, b plus DoMath c minus DoMath 5 times 4. Something like that. So this would give me a 20. We actually don't know what C is here, but you know, it's some variable. So this would be whatever the value of C is minus 20. And then this will be whatever the value of B is plus the result of that. So for the homework, you can assume that all math happens, we're going to say left to right, where a DoMath expression fully resolves before its value is given to any higher expression. So that is to say, you do not need to handle order of operation, which means that you don't have to treat multiplication as being more important than addition. Just do it in the order that it showed up. Now, my hint to you, this shouldn't be overly difficult. My hint to you is, remember, this is the left expression. This is the right expression. This is the left expression. This is the right expression. So when you boil down expressions, you're going to have to make sure that you handle their full resolution. When you get the value of the expression C, you're going to resolve that value. When you get the value of DoMath 5 times 4, you're going to have to call get the expression value on that and handle that. Okay, I think you'll find you have to add very little to our project in order to get this to work. Go ahead and put this. Right now. Actually, let's do all of this for right now. This is homework 6. Okay, that's due on Wednesday by 10 a.m. And then I'll go ahead and say updated for initial DoMath expressions. Now you have the latest version of my code. All right. Any other questions about what I'm asking you to do for Thursday? Okay. Well, I will see everybody at 10 a.m. on Thursday.
Thank you.
Thursday or Wednesday?
Yeah, sorry, 10 a.m. Wednesday. 10 a.m. Wednesday. Thank you.
It's in-person class or online class?
But the plan is in person. I have a feeling the university, I mean, I haven't heard anything, but I have a feeling since the number of cases has been going up that they might put some sort of rule against meeting in person. I don't know, but for right now, we're planning on meeting in person. Go that route.
Okay. Yeah.
All right.